Good afternoon, everyone. Welcome to the ninth class of reagents is organic synthesis. In this class, I am going to discuss about copper-based reagents, chromium-based reagents, manganese and zinc-based reagents, and lastly, I am concluded by mercury-based reagents. So first, I am going to discuss about copper-based reagents. In this case, first I will discuss about the most important reagent, that is the Gilman reagents or Gilman reaction. So here, what happened? In a alpha beta unsaturated ketone, this kind of organocopper reagents undergo a 1,4 Michael addition rather than 1,2 conjugate 1,2 direct addition. So, what is the mechanism of this reaction and why this copper reagent at 1,4 fashion, not the 1,2 fashion that we are going to discuss? Uh, First, this copper kind of organoreagent such as R2CuLi or R2CuMgBr. So anything R2 can be aryl or this kind of dimethyl Me2CuLi or any kind of allyl. So what happened in this case? This kind of alpha beta unsaturated ketone. This is the hard position. This is the soft position because this undergo resonance. So because of this resonating structure, this position is hard, soft, and this position is hard. In the copper case also, due to the presence of transition metal compound, so this methyl electron can be resonant on the copper vacant d orbital. So that's why it is also soft reagent. And due to the soft interaction, 1,4 addition happens. So first, what happened? First, there will be a interaction of this double bond with the copper through oxidative addition. So that R group, whatever is there, so first oxidative addition happen and followed by reductive elimination. Oxidative addition followed by reductive elimination, giving this product. So that's enolate, and then after that acidic workup giving this product. So the pseudochemistry can be distinguished by the group which is available. So if it is the in alpha orientation, so the methyl group which is coming from the beta position. So this is the attack. So this axial attack giving the beta oriented product. So due to this is due to the minimized steric hindrance. So this is also in this case this oxygen group is the beta, sorry, alpha. So that's why this coming from the beta. So beta product we are getting. Now I'm going to discuss about 1,4 tandem addition and allelate trapping by copper reagent. So in presence of copper and magnesium and any kind of R, 1,4 addition happen, not the 1,2, 1,4 addition over 1,2 addition. This is due to sub interaction. So first R2 attack here. So I'm just writing like this way. RCULI. So R mine attack here and form this enolate. O minus R. Now there is a two possibility. We can trap this enolate through O attack or C attack. So if we treated this kind of enolate with salivating agents such as TBS triplet, TBS chloride, TMS chloride as carbons and silicon or carbon and oxygen and silicon. Between this oxygen silicon bond is more stronger. That's why first it no it will keep trapped with the silyl. So in presence of TMS triplet, it will trapped with the oxygen trapped with the silyl, not the carbon. So O attack prefers. Now if we treat it with any kind of electrophile such as methyl iodide. So this is trapped with the so if you treat it with methyl iodide, so it will trap with the carbon bond. So the such like this one, trapped with the carbon. So this is due to the carbon-carbon bond formation over carbon-carbon bond formation over carbon oxygen bond formation. So, so this is the two type of addition. So after forming the enolate, then enolate can be trapped through O or through A carbon. So if it is such like silylatic agent, TMS triplet, TMS chloride, TBS triplet, TBS chloride, so that form or TMS bond due to the oxygen silicon strong bond. But if we treat it with any kind of electrophile, such as methyl iodide, um, or any kind of anything electrophile that can be formed the carbon carbon bond due to the strong bond of carbon carbon rather than carbon oxygen. So if we treated any chiral ligand, so if we treated this kind of chiral ligand in the presence of copper, this ligand, so what happened? This C3 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 MgBr with the copper form the first copper complex. Then 1,4 addition happened and followed by any kind of Rx, this enolate trapped with the R. So if we treated this compound with the chiral ligand, so that at this attack should be on the chiral phase so selective manner. So in also selective fashion. So that's why we will get this kind of enhancer selectivity or ratio selectivity. Now I'm going to discuss about allylic alkylation by copper reagent. So this is the allylic compound. So R prime double bar R double prime. So this is the allylic acetate. So this alkylic of allylic acetate in presence of copper undergo two type of product, alpha or gamma. So this is alpha, beta, gamma. So this allylic is substituted products in presence of copper can form two type of product, alpha product or gamma product. So first copper undergo allylic this kind of pi allyl complex. So first oxidative addition of this copper through this pi bond happen and followed by leaving group elimination giving this pi allyl complex. So this is from this kind of pi allyl complex in the presence of copper. Now, there is a two possibility through alpha attack or through gamma attack. So, if the copper compound is substituted with electron withdrawing group such as cyano or Cl ligand, so that form gamma attack product. So, this one. If the copper complex is treated with very strong hard reagents such as any kind of hard reagents, RLI or RMGBA that giving the alpha product. So this is giving the gamma product, and this is giving the alpha product. This now I'm going to discuss about Ullmann reaction. So this is the coupling reaction in presence of copper powder. So what happened in this? Two kind of alkyl halide coupled and give this symmetrical or unsymmetrical biaryl compounds. So this is the any kind aryl halide. It may be Rx. X could be bromide, iodine. So this is the if this is coupled together, then this will give the symmetric biaryl compounds. If this both this one and this one are different alkyl halide, this will give the unsymmetrical biaryl compound. So that can be possible via two pathways, via radical pathways. So which involve copper 0 undergo copper 1, and that radical will couple to each other forming this aryl aryl bond, or involve aryl copper intermediate. So this is the different mechanistic pathways. Now I'm going to discuss about chromium based reagents. So first I'm going to discuss about Fischer carbene. So Fischer carbene is basically the chromium based carbene. So penta carbon monoxide, any kind of R. So this kind of compound is called Fischer carbene. So this is the carbene center. So it is electropositive, and this is metal is electronegative. So the movement should be like this way. So this is the driving force, this oxygen or this kind of heteroatom. So this X is the heteroatom, any kind, oxygen, sulfur or nitrogen. So this pushes the electron like this way and giving this negative. So this chromium would be negative like this. This is the resonating form. So how it will be prepared? So hexacarbonyl chromium in presence of RLi giving this compound. So this under any kind of uh, hard alkylating agent such as methyl iodide. So this is hard. This giving the hard added product or any kind of soft methyl alkylated product. So this such as CH3COCl. So this is the soft because this is anaerobic resonance. So this will be give the this kind of product. So this is the Fischer carbene. So now we can discuss about the reactivity. So this is chromium center. So this is so if we consider the resonating structure, so it will go this way and this way. So nucleophile can attack this position, or as this X is any heteroatom, so it can attack through an electrophile through its lone pair of electron. So this can be attack on a electrophile. So this can attack on a nucleophile. So now, if this center is methyl or any carbon which has proton available, if this compound has proton available, then any kind of base abstract this proton. So this is the another reactivity. So if we consider this allyl chromium complex, so if this is the nucleophile attack can possible here and here. So if we treat it with a nucleophile, so it can attack either 1,4 fashion or direct 1,2 fashion. Or if this carbon is an aryl group, so nucleophile can attack of para position and ortho position and directly to the chromium center. So now I'm going to discuss about the nucleophilic reaction of chromium carbene. So this is the chromium carbene. So now this is the aryl group. So if we treat it with such as methyl lithium, so methyl minus lithium plus, just I'm taking this way. So it is directly attack to the this center. So this is the nucleophilic position at that, and after treating with HCl, so this should be the lone pair of the oxygen reacted with H plus and followed by liberation of methanol giving this related product. This is the nucleophilic attack. Now I'm going to discuss about the basic behavior of the chromium carbene. So if in the previous cases this methyl was aryl such as phenyl, but in these cases this is methyl, so it has proton. Now if we treat it with base, so this proton could be abstract by the base and that can undergo resonance. So it will giving this product. Now, if we treat it with any kind of electrophile such as benzaldehyde, so now this will go like this way, and this enolate react with the benzaldehyde and forming this compound O minus. So here, what happened in this case? This case is this O minus is struck by the silylating agent. So TMS silyl they have used. So this methyl silyl react or oxygen react with the silicon. So because of the oxygen silicon strong bond, so it will form this one double bond with T. Sorry, one carbon will be there. Missing one carbon. This one O Si Me3 is. Now the system has triethylamine as a base, so base abstract this proton and elimination happen, giving this product. This is also an example of that basic nature of the chromium carbene. So N-butyl lithium is base, so it will abstract this methyl proton and 1,4 attack happen here. So 1,4 attack giving that enolate, and that enolate was treated with ammonium chloride. So that is quenched and giving this product. So this is the nucleophilic behavior of the chromium carbene. This is the basic behavior of chromium carbene. So now I'm going to discuss about manganese based reagent. So manganese basically used as a reductant. So what happened in these cases? I'm going to discuss about organomanganese reagent. So any kind of organic reagents such as halide or alkyl halide, so treated with the manganese, giving this manganese reagent. So R MnX or ArMnX. So manganese in the MTBA ether solvent. So this is a ether solvent giving this manganese as allylated manganese iodide product. So this is the organomanganese compound, organomanganese, just as organocopper reagent or organolithium reagent, manganese. So this is as a manganese is metal, so it will be partially positive and this should be partially negative. So now if we treat it with this compound with benzaldehyde, so that negative charge react with the benzaldehyde giving this alcohol. If we treat it with the ketone, then directly attack on the ketone giving this tertiary alcohol. If with reaction manganese with aryl iodide and palladium, so that there is a possibility of coupling reaction. So just as boronic acid, so this is the manganese compound, so it will also couple and giving this coupled product. Also organic, same as manganese compound, I'm going to discuss about organo zinc compound. So this is same, just like manganese, this is also organic zinc compound. This is partially positive zinc and this is partially negative. So that R minus can attack with the acyl chloride, 1,4 acid, coupling reaction or alkylation reaction. So giving this kind of product. So this is the another kind of behavior of dimethyl zinc. So this dimethyl zinc. So if we treat it with dimethyl zinc in THF solvent and any kind of imine, so it will give this product. This is the major product. So whatever I'm discussing here, zinc used as a nucleophilic behavior of the alkylating agent I am discussed, but here this kind of dimethyl zinc used as a radical reaction. So that can be used as a radical. So what happened? First, dimethyl zinc in presence of oxygen undergo a methyl radical reaction. Methyl, it will form methyl radical. So now this methyl radical with that this is the THF tetrahydrofuran. So this will radically clip, and from this methyl radical and this radical undergo CH4, methane and methanol form, and this will the radical form. Now this radical in presence of imine. So radical this radical react with this imine and form this radical. So now same this radical is quenched with water and giving this the product. So here in presence of a dimethyl zinc radical reaction happen. This is the Simon Smith cyclopropanation by zinc copper reagent. So any kind of disubstituted aldehyde, disubstituted alkene or tetrasubstituted alkene in presence of zinc copper alloy and diiodomethane or diethyl zinc or diiodomethane giving the cyclopropane. Disubstituted or tetrasubstituted cyclopropane. So if it is Z alkene, we will get the cis cyclopropane. If it is E alkene, we will get the trans cyclopropane. What is the mechanism? I am going to discuss. So first, zinc in presence of di CH2I2 diiodomethane from this ethyl zinc iodomethane. So now this ethyl zinc iodomethane in presence of alkene undergo this cyclopropane butterfly transition state. So what happened? This CH2 react with this pi bond of the alkene, and this is coordinated with the iodine and zinc compound. So after liberation of the ethyl zinc iodide, we get the substituted product. So if any compound has this kind of directing group, OH or OMe, if we treat it with this uh, ethyl zinc complex, so what happen in these cases? In these cases, if it is beta phase, the attack cyclopropane forms from the beta phase due to the chelate formation. So this is the chelate it will form. So it CH2, it will also attack from the beta phase. So because of zinc and oxygen coordination. So this due to this reacting groups, here is alcohol or OMe. So this attack from the same phase. So it will give the beta cyclopropane product. If the any kind of chelating group are there, the cyclopropane from the same phase. Now I am going to discuss about oxymercuration demercuration reaction. So these go under SN 2000. So in presence of mercuric acetate and NaBH4, we get this alcohol. So what happened in this case? Alkene undergo reaction with the mercury from this uh, mercuriated cyclopropane product. Now there is a two possibility. So if we treat it with this compound with water, so it will go like water can be attacked from this side or this side. So it will attack from the more substituted side. Why? Because of the stability of the carbocation. So if it, there is a two possibility. One is that water attack here and carbocation form here. Another is that carbocation form here and water attack here. So this is the SN2 attack. So the carbocation stability also matter. So here also, so if this bond broke, there will be this carbocation will be tertiary carbocation. That is more stable. That's why attack preferentially occur from this side. So this is the form after NaBH4 treatment will give this alcohol. So the H minus attack directly to the carbon and liberate the mercury. So this will give the demercurated product. First is the oxymercuration. So mercury and oxygen attack, and after that demercuration of NaBH4. Now I'm going to discuss about some problem. So first, this alpha beta unsaturated ketone in presence of phenyl magnesium bromide, this phosphine compound and copper, what would be the product? So this is the it first THMgBr in presence of copper from the Gilman reagents. So PHCuMgBr. So now this can be soft. So if MgBr is there, this will be hard reagent, but if in presence of copper, it is salt. Due to the salt behavior of the phenyl group, there is a possibility of 1,4 addition. So because this is a soft center and this is the soft, so soft interaction happen. So now it will give the pH will attack here and that will go and this O minus ON. So now if presence of water or solvent, so it will quench. The negative charge will quench. ON pH. Now the what will be the stereochemistry of the pH. So here we can see that this chiral ligand has this methyl group, here is the beta orientation. So the copper complex, whatever is the form, so this will be the copper, magnesium, this is the ligand, the phenyl ligand, phenyl phosphine ligand. So this will, and this is the pH. This is the, this will form from the beta orientation. So as this methyl is the beta, so this attack also happen from the beta. That's why we are getting the beta is a major product. As this methyl is a beta orientation, the 1,4 attack should happen from the beta orientation. So because copper undergo a ligand exchange reaction with this chiral ligand, so the right answer will be the first one. So this is the alpha. So this not happen. So this is 1,2 attack both. This is not possible. So in this case also, the next question, also copper reagent. So Gilman reaction happen. So 1,4 attack this way, giving the enolate. So if we did, so all reaction this methyl is beta. So to reduce the steric index, the attack happens from the alpha. This is the basic reaction because in cyclohexane, this is the cyclohexane. If it is in beta, the attack should be happen from the alpha. So this is the alpha position or the axial position. This is the equatorial position. So to reduce the steric hindrance. Now this will form this enolate O minus. Now this enolate is treated with methyl silyl chloride and triethylamine. So now there is a presence of acyl Me3Cl. So now there is a two possibilities: oxygen attack, O attack, or C attack. So this can go like this way or C attack. C attack. But as oxygen silicon bond is highly strong, so that's why O attack prefer rather than C attack. If there is an electrophile such as methyl iodide, then C attack would be preferred. But as this is the silyl group is there and the oxygen silyl bond is very strong, that's why C attack happens. So Me3 SiCl will give the silyl attack product. So this is beta. This should be from the alpha. this will give the O SiMe3. So the right answer would be second one. Now the next question. Also Grignard, this is the Grignard reagent in presence of copper. So it will form Gilman reagent. Now in presence of copper, soft interaction happens, so that will attack to the 1,4 asa. 1,4. In presence of Celium, Cerulean, so Cerulean I use as a Cerium used as a Lewis acid, so it will activate the oxygen. So Lewis acid base, the oxygen has lone pair, so it will react with the cerium. So then one to attack paper, so it will more electrophilic. This is 1 2. So what happens if it is attached to 1 2 person? Then this will come OH, methyl, and ethyl. And if it is react with 1 4 addition, so ethyl group CH2 CH3 group react. CH2 CH3. The right answer is the first one. X is the 1 4 attack product. Y is the 1 2 attack product. The next reagent is also a Gilman reagent. So 1 4 attack happen. So dimethyl Me2 CuLi. So methyl minus directly react with the 1 4 person. So I'm just writing like this way. Methyl minus react with the 1 4 person. So it will form this negative charge. So So this is the methyl from the copper compound came, then CO2Me, and then negative charge. Now what happened? This negative charge can react with the carbonyl. This will go, this will come and liberate this OMe. So methanol minus methanol will leave from the system. This will give them, sorry, 1 2 3. I'm missing one carbon. On this carbon I'm missing. Methyl CO2Me. So the right answer will be the option 2. So I guess this is clear. First, methyl undergo 1 4 attack. So this is a 1 4 attack because of the copper reagent. Then followed by this negative charge directly react with the carbonyl compound, giving this cyclopentanone. Now this is the Fischer carbene. So now I have to check the nucleophilic and electrophilic position of the Fischer carbene. So this is nucleophilic. Nucleophilic. This is also nucleophilic. OMe is a electrophilic. Now here CH2 minus is minus Li plus. Also here O minus Li plus. So both are this is the negative charge. So if we write in this way, OC5Cl double OMe furan and treat it with this O minus Li plus CH CH2 minus CH2 minus Li plus. So now this undergo reaction is this way. This is the nucleophilic position. So and from this, now what happening in this case is OC whole 5 double one OMe. So this is undergo resonance. Cr minus double one, that is the furan. Then CH2, this methyl CH and O minus Li plus. Further, this come this way and neutralize uh, like this. This will go give this product OC whole 5 Cr double one OMe CH2 CH2 furan pH O minus Li plus. Now this O minus react further with the carbene and this will go. This will form 1, 2, 3, 4, 5, 6, 6 member ring. Oxygen. This is the chromium minus CO5 followed by ONE. CH2 furan CH2 H. Now, now what happens? This will come and leave this ONE. So it will liberate a minus methanol. This will give this product. Oxygen, double bond, chromium, CO whole 5, furan, and phenyl. Phenyl, furan. So this chromium and phenyl, between this there is oxygen. So chromium, phenyl, and furan. So this is the right answer. This is not possible because oxygen is between chromium and phenyl. This is oxygen is chromium and furan. Not possible. In this case, oxygen is between chromium and phenyl. This case, oxygen is between phenyl and furan. Not possible. This is not possible. So option B is the right answer. Now the next question. So in butyl manganese chloride. So manganese can also act as a Lewis acid. So between or this is the manganese Lewis metals is electropositive. This is electronegative. So between aldehyde and ketone, aldehyde is more electropositive or more reactive than ketone. This is less reactive. So the N butyl should react on the aldehyde rather than ketone. because of the electrophilicity. So the right answer will be this one. So aldehyde react on the uh, N-butyl group react on the aldehyde center. So ethyl C double one two CH2 CH2 OH N-butyl, and there is a hydrogen. So option C is the right answer. Six. Now this is also a fissile carbene. So this is the fissile carbene. So now here this methyl has a proton. Now this proton can be abstract by base. So if we treat it with N-butyl lithium, so this is the three proton of the methyl. Butyl minus lithium plus. So now this butyl minus react with the proton and form the negative charge. So abstraction of proton happen. This will form CH2 minus Li plus. Now what happens? If we treat it with this with benzaldehyde in CHO. Now this CH2 minus react with the benzaldehyde and form methyl. This is C double one two nitrogen. This is the chromium one, chromium CO5 and OH pH. So this is the uh, beta orientation. So to avoid the steric hindrance, it will come from the alpha orientation. This one. Now this treated with acetic acid. Acetic acid. So under acidic condition, this chromium carbene from the clip from the ketone. So it will clip to ketone. It will come this one. What will be the right answer? First one? Yeah, first one. Now the next question. This is the Simon-Smith reaction. Simon-Smith reaction or cyclopropanation. Cyclopropanation. So under diethyl methyl and zinc copper cyclopropan happens. So as I discussed previous, so it will form this complex. As this is the directing group is there, or this is the chelating group, so the cyclopropan should happen from the up beta orientation. This is the zinc and iodine ethyl. This chelate formation happen clearly written. Zinc, iodine, ethyl. So this chelate formation happen. So this is the oxygen as lone pair. So this chelate formation happen. So that's why it is a beta. So cyclopropan should occur from the beta. If cyclopropan occur from the beta, the hydrogen will be the alpha. So this is due to the chelating chelation chelation of the ore and zinc. So the cyclopropan upside and the hydrogen go to downside, right? So the right answer is both. One is R equal to H and one is R equal to methyl. Both the cases same. So we'll get this one. A is the right answer. So this is due to the chelation, just like this one. So CH2, just I discussed here. So this kind of chelation form. Now this is the oxymercuration demercuration reaction in presence of zinc acetate. What happened? First mercury complex form, then water attack H2. Now the possibility water attack from this side or this side. So the stable carbocation from where? That side water attack. So this is if this is the carbocation from this will be tertiary carbocation, this will be the secondary carbocation. So water attack from this side. That is the stronger carbocation. This go through stability of the carbocation or stability of the carbocation. Carbocation or Markovnikov attack happen here. Markovnikov. Markovnikov reaction happen. So this will give then OH mercury. Now in presence of NaBH4, the hydride react with the this center and leave mercury. So this will give this product. Now the stereochemistry. So this is cyclohexane. So if we write in a chair cup, chair cup, if we write. So to avoid steric hindrance, the tertiary butyl group come in the equatorial position definitely. So this is the equatorial position, this is the axial position, actually is the hydrogen. Now 1, 2, 3, 4. 1, 2, 3, 4. There is a two possibility. Methyl will come in the this one. Methyl is the equatorial and alcohol in the axial, or another one. Methyl is the equatorial and alcohol axial. So which one happened? So if we did, write in this way, so here hydrogen is there. So 1, 3 methyl and hydrogen interaction happen. 1, 3 methyl hydrogen axial interaction happens. So this is, so here is 1, 3 axial interaction, axial interaction that hindrance happen. But in these cases, no such hindrance, no such hindrance are there. That's why this is not possible due to the 1, 3 interaction. So the right answer will be this one. Now, mm, the number 10 is the dimethyl zinc. So in place of dimethyl zinc and THA will undergo radical reaction. So dimethyl zinc, dimethyl zinc in presence of oxygen undergo a radical reaction from methyl radical. So dimethyl zinc in presence of oxygen undergo a methyl radical. It will form methyl radical. So then radical react with the THF tetrahydrofuran. So this is a tetrahydrofuran. So this is radically flipped and form methane and tetrahydrofuran radical. This radical plus methane. Now in the system has imine. Oh, now the system has imine. So this is the pH double bond NTS. Now there is a possibility of one to attack of this radical with this imine. So that will give pH NTS minus, and that purine at furan tetrahydrofuran attack compound. Now under acidic workup or in presence of water, it will give the tetrahydrofuran added product. So pH NHTS protonation happen in presence of water. And we'll leave this one. So the right answer would be the option B. So this is the 10 question which I have for today. So if I summarize it, the first is the Gilman reaction. So this is the phenyl in presence phenyl magnesium bromide in presence of copper undergo 1,4 addition due to the sub-sub interaction. So in this case, the stereochemistry method in the chiral ligand, this methyl group is the beta orientation. So this copper complex form from the beta complex form. So attack should happen from the beta, and we'll get the beta attack product. In these cases also, one could adapt happen. So in all the compound, this methyl is beta. So to reduce the steric index, the attack should happen from the alpha. So this is the alpha attack, one core attack, and after that, trimethyl chloride they have used. So between now there is a two possibility: ortho attack and carbon attack, oxygen attack and carbon attacks. Oxygen silicon bond is very strong, so oxygen attack happen and giving the product rather than of carbon silicon bond. The next question is also 1,4 attack and then 1,2 attack. So in presence of copper and ethyl magnesium bromide, 1,4 attack happen. In presence of ethyl magnesium bromide and cerium, 1,2 attack happens. So cerium form complex with the oxygen, Lewis acidic behavior of the cerium. So favor the 1,2 attack. And copper due to the soft interaction favor the 1,4 attack. Also the dimethyl copper and lithium. So this is also 1,4 attack followed by the trapping of the negative charge with the ester giving this cyclopentene. Next question is the Fischer carbene. So this is the two nucleophile here. This is the carbon nucleophile and this is the oxygen nucleophile trapped with this nucleophilic position and this nucleophilic position of the Fischer carbene via this mechanistic way. And next question is the manganese. So this is the Lewis acidic behavior of the manganese. So manganese this N-butyl is a electro negative, so that react on the aldehyde center rather than ketone center. So aldehyde is more electrochemically positive, so it will react in the aldehyde center rather than ketone center. The second question was this methyl is there is a methyl, so in presence of Fischer carbene in presence of butyl lithium, so this is methyl proton abstract from Ch2 minus, the negative charge react with the aldehyde from this alcohol. So as this phenyl is the beta orientation, so to avoid steric index, we'll get the alpha attack alcohol and followed by the carbon acetic acid reaction, this carbene lead and from this ketone. Next is the Simon-Smith cyclopropionation. So in presence of directed groups such as OR or OH or O-methyl, so cyclopropane occur from that phase. So it is the beta, then cyclopropane occur from the beta phase due to this zinc coordination. So zinc and oxygen coordination or the directing group of the OH from the same direction. So that's why we are getting the same directed product. So next is the oxymercuration, demercuration product. So here also the after oxymercuration, the stability of the carbocation depends. So the more stable carbocation uh, attacked water. So attacked by water. So this is the more stable carbocation. So this was attacked by the water and between the stereochemistry. So this due to the 1,3 axial interaction, there this product is favored. And this is the dimethyl zinc radical behavior. So after dimethyl zinc in of oxygen from methyl radical, this under trapped with the furan, from furan radical, and that will react with the imine and giving this imine furan adduct product. So if you have any question, you can ask. Otherwise, I'll close the session. Okay, bye.